This chapter covers basic chemistry. It's titled The Nature of Molecules and the Properties of Water. So your learning objectives for this first section is to define an element based on its composition, to describe the relationship between atomic structure and chemical properties, and to explain where electrons are found in an atom. So matter, by definition, is a substance which has mass and occupies space, which is what most substances are. All matter are composed of basic units that we call atoms, which is a structural unit of matter. Now, understanding the structure of atoms, it's critical to understanding the nature of biomolecules. So we're going to explain anything that happens at the cellular level or higher. It's useful to know what's going on at the chemical level. So chemistry is a foundation for all of biology. So looking at an atom itself, which is the basic unit of matter, atoms are going to be composed of subatomic particles. And we're going to have two general regions. You're going to have an inner region called the nucleus, and then an outer region called the electron cloud. And in the nucleus, you're going to find positively charged particles called protons. And we're going to be symbolizing protons with a P and a plus symbol. So that'll be your symbol for protons. Neutrons are also going to be found in the nucleus, but they are neutral particles. And we're going to symbolize neutrons with an N and a superscript with a 0 to indicate neutral and no charge. Now, outside of the nucleus, we're going to have electrons, and they're going to have a negative charge. And so we're going to symbolize those with an E with a minus, superscript of a minus. And so these are going to be found in the space, which are going to be called orbitals, surrounding the nucleus. When we look at the atom itself, it's mostly empty space. If we were to compare, and this is what the evidence suggests, so if we were to scale up an atom to the size of say a stadium where we play football or soccer, if you took a coin like a dime or a nickel and you put it right in the center, that would be the nucleus. The rest of the stadium would be the space where we would find electrons. And so electrons are very tiny, and so the atom then is viewed as mostly empty space, which is pretty amazing. So over here on the bottom right, you might recognize down here the periodic table. The periodic table is a listing of all the different kinds of elements, and each box has certain symbols in there. And the first symbol is called the atomic number, which is a whole number there. That's going to be the number of protons, okay? And we're going to call that again the atomic number. And when it comes to regular atoms, they're going to have basically the same number of protons and electrons. And that means if an atom like helium has 2 protons in the nucleus, and it's also going to have 2 electrons or 2 negative charges in the orbitals outside. So the +2 and the -2 cancel each other out, making atoms neutral. And going back to that atomic number is going to tell us the number of protons that you're going to find in the nucleus. So if we look over here and we looked up helium in the periodic table, that whole number 2 tells you the atomic number, which is the number of protons. And by the way, the periodic table, if you start on the first row and you go left to right, they're arranged in order of increasing atomic numbers. So hydrogen right here would be number 1. Then helium number 2. We got to the end of the first period, and the second one, lithium would be number 3. So its atomic number would be number 3. So if we zoomed in there, you can see the whole number in the box right there is 3. So you can identify the element by the number of protons. So that's what it says right here. Every atom of a particular element has the same number of protons. So what is an element then? This is another vocabulary word to consider. It's any substance that cannot be broken down by to any other substance by ordinary chemical means. That means if we took something like water, which is made of 2 atoms of of hydrogen, 1 of oxygen. We can break that down. But once we broke it down, we're going to get to 2 hydrogen atoms and 1 oxygen atom. You can't break those down any further by normal chemical means. And so this is the fundamental units there, the hydrogen atoms and the oxygen atoms. Those are atoms of a particular element. You can't break it down any further by normal chemistry. Atomic mass is another consideration. And some of the terminology is a bit confusing, so we'd want to be very careful. There's a difference between mass and a difference between weight. Now, mass is going to refer to the amount of substance you have. So if you took a brick and nothing changed from that brick, and you take the brick and you move it from Earth to the moon, it's still going to have the same amount of stuff in there, same amount of substance. So the mass would be the same, but the weight would be different. The weight is different because weight is it's the force of gravity, and since the moon has less gravity on that mass, still the same mass but less gravity, then the weight would differ, but the mass would be the same. Okay. Now, I think the book and these notes confuse the difference between atomic mass and mass numbers. So right here in the notes, you're going to want to scratch that out and rewrite it as mass number. Okay. And so this is the actual definition for mass number. So in an individual atom, the mass number is the sum of the protons and the neutrons. We can write that as a formula, which will be useful. So make sure you write this formula in your notes, and then you know how to use it. So the mass number is equal to the number of protons plus the number of neutrons. Okay. That's different than atomic mass. The atomic mass is given in the periodic table, but the atomic mass is something different. And so I'm going to define that for you here. The atomic mass, which is the actual definition and what you see in the periodic table, is the number. It's not the number, actually. It's the average mass for atoms of an element. It turns out that there are different forms or different atoms of this, types of atoms for the same element. Now, for an element, they have to have the same number of protons, but the number of neutrons can vary. So for helium, helium has an atomic number of 2. That means it has 2 protons. That would never be different, but it can have a different number of neutrons. Okay, so the mass numbers would be slightly different. If you have more neutrons, you're going to be heavier, but you're still going to be helium because it's the number of protons that identifies you. So helium would always have 2, and if the helium atom had 2 neutrons, then the mass number would be 4. But let's say you had a helium atom that had 2 protons. That's what makes it helium, and its mass number was 5. Then what would the number of neutrons be? And in this case, we would solve there. We could say that that would mean that another kind of helium atom would have 3 neutrons, and that 3 plus 2 would be equal to 5, right? So and we're going to see this over and over again. And the way we might symbolize mass number is to take the atomic symbol, which is what you see in the periodic table, like helium is He, and you can write the mass number. So for the 2 helium atoms I described, helium 4 would be a helium atom that has 2 protons and 2 neutrons. And then we just did a calculation that told us for helium 5. As I indicated to you, let's say you had an atom over here with a mass number of 5 and 2 protons. It's helium, but it's a helium that's a little bit more massive. It has a mass number of 5. Okay. We're going to see that these are called isotopes later, and I'll tell you more about that later. For example, carbon has 3 isotopes, carbon-12, carbon-13, and carbon-14. Now, the atomic number for carbon is 6. Okay, so we can tell then if carbon has a mass number of 12 and carbon has to have 6 protons, then what's the number of neutrons? It would have to be 6. 6 and 6 equals 12. Carbon-14 would be the heaviest element. Not element, I'm sorry, heaviest isotope of carbon. I'll define isotopes for you in a little bit. Now, it's important to note that each proton and each neutron has a mass of approximately 1 Dalton. And a Dalton is the same as an AMU, which stands for atomic mass unit, which is why over here in this diagram that I shared with you on the right that shows one of the boxes of the periodic table, it says AMU for atomic mass units. This is the unit they use to measure very small particles. Because the neutrons and the protons are about the same mass, 1 Dalton or 1 atomic mass unit, that's why the formula for mass number is number of protons plus number of neutrons. All we do is add up the number of each, and each one is technically equal to 1 atomic mass unit. So a helium-4 atom would have a mass of 4 AMUs, or 4 Daltons. Now electrons, they are negatively charged particles, and they're going to be located in outside of the nucleus in an area called orbitals. Now neutral atoms are going to have the same number of electrons and protons, which we already mentioned. So if they're neutral, then the number of protons and the number of neutrons is the same. But what happens if an atom loses or gains electrons after it was neutral? So it's neutral, same number of protons, same number of electrons. But sometimes in chemical reactions, your atoms gain or lose electrons. And that means they're going to gain or lose negatively charged particles. Right? So in this case, if that happens, we're going to end up with charged particles called ions. Okay? In general. And now you're unbalanced. So an atom is balanced and neutral, but an ion is a charged particle. There's two kinds. There's the cation, which will have a net positive charge. And then there's an anion, which will have a net negative charge. And here we see an example of sodium and chlorine. Now sodium has the number of, if we went back and looked in the periodic table, now sodium would have a total of 8, 9, 10, 11. Would have 11 protons there, and then it's going to have 11 electrons. Now chlorine is going to have a total of 17 protons in the nucleus, and would have to have 17. And those little dots that are on the outside right here represent electrons. And what we're seeing here is a transfer of electrons during a reaction between a neutral sodium atom and a neutral chlorine atom. And these numbers down here just represent the number of electrons that it has at the different energy levels. Each energy level is a ring. Here, the innermost energy level holds 2, then 8, and so on. But right now we're seeing the normal neutral atom in this diagram. When the electron gets transferred during this chemical reaction where we react sodium with chlorine, both are neutral, the sodium, being a metal, is going to lose its electron, and it'll come over here into this energy level for chlorine. And that means sodium is losing one of its negative charges, one of its electrons, and chlorine is gaining an extra negative charge. Now, sodium was neutral before, but it loses a negative, so overall that's going to make us a positively charged particle. In this case, our positive sodium ion. Because chlorine gained an extra electron, it now has an extra negative charge because that electron shifted into its energy level. And now the chloride ion, the chlorine atom now has an extra negative charge, so now it is a chloride ion. You can see the numbers changed here overall from before. The sodium had 1 electron in that outer energy level, now it's missing it. And then over here, chlorine had 7 in its outer energy level, but now it has 8, it has extra. So overall now we have a cation here for sodium and an anion for chlorine. Now these negative charges and the positive charges are opposite, so they attract each other and a chemical bond is formed between them called an ionic bond. Okay, so these are the way cations and anions form. Remember that a cation is going to have more protons and electrons. That means more positive charges than negative charges. The only way that'll happen is if an atom loses electrons, because it's supposed to be balanced before the loss. An anion is going to have fewer protons because it's going to gain an extra electron. That gives it a negative charge. Now, a quick way to predict this is if you look at the periodic table. So I'm going to draw a quick periodic table here. And if I were to draw a little line right here separating the left and the right looks like a staircase. Anything to the left is metals, and anything to the right is non-metals. The metals tend to lose their electrons, and the non-metals will gain electrons. Okay, so when we talk about losing and gaining, it's the metals. So sodium is found over here. It's right about there on the periodic table, and chlorine is right around here. So basically, sodium loses its electron, whereas the non-metal chlorine is going to gain the electron. So good prediction. Anytime you see a metal and a non-metal reacting, the ions are going to form and an ionic bond will form. I mentioned earlier the term isotopes. So isotopes is going to be for the same element. So any single element, it's going to have the atoms in that within that element. If you get a natural sample, it's going to have atoms in there that are going to have different number of neutrons. Okay, so the neutrons can be different. The number of protons cannot, because the protons identifies the element. So for example, carbon on the periodic table, and if we went back to that periodic table, carbon, which is right around here, where I'm circling there, it has an atomic number of 6. So in order to be carbon, it's always going to have 6 protons in the nucleus. Okay, and so we do have a diagram here that shows a carbon 12, carbon 13, and carbon 14, which I mentioned earlier. We can symbolize them easily by saying C12 using the atomic symbol and then the mass number, C13 and C14. And if I ask you to use the formula for earlier, where the mass number, which is that number that I wrote after the symbol, C12, C13, C14, those are the mass numbers. And I asked you to tell me how many neutrons carbon 14 has, you can use this formula. And in fact, you should be able to do this on a quiz or a test. I'll ask you how many neutrons it has. So I say, here you have carbon 14. How many neutrons does carbon 14 have in the nucleus? All you do is substitute the numbers in there. 14 goes here for the mass number, and then on the periodic table you look up carbon and you note carbon has an atomic number of 6, so you put the 6 there, and now all you have to do is solve for the number of neutrons. And if you did that, you're going to get a total of 8. So 8 would fit in there. 8 and 6 gives you 14. And that would be this isotope right here. It's carbon because it has 6 protons in the nucleus. The number of neutrons can vary. And remember, the number of electrons of your neutral have to be the same. So 6 protons, 6 electrons, right? For carbon 13, it's going to have one less neutron than carbon 14 did, so it'll be a bit lighter. It'll only have a mass of 13 atomic mass units. But here you can use the formula again, this one right here, to figure out how many neutrons it had. And if you did, you would see that the answer would be, for the number of neutrons, would be 7. Now, carbon 12 is the most common isotope. Now, and then again, the word is isotope. It's the most common isotope for carbon. Now, when it comes to isotopes of a given element, when the nucleus gets too big, depending on which element we're talking about, the nucleus is going to be unstable. In this case, 8 neutrons is too much for carbon. So carbon itself, and put a little star right there, carbon 14 is radioactive, and that means that the nucleus breaks apart and gives off radiation or radioactivity. Now, for a given isotope, and a given isotope could be carbon 14. It could be uranium, which is a very, very heavy metal, uranium-238. It is going to be a radioactive isotope. These isotopes have a half-life, and that means it's the time it takes for one half-life of the atoms to decay. So for half of the radioisotope in the sample to decay. So let's say that you had in a sample you had 10 grams of, or 100 grams to make it easy. You had 100 grams of carbon 14 in a big sample of carbon. It's mostly carbon 12, but there's about 100 grams of carbon 14 in there. After one half-life, the bottom axis is time. After one half-life, half of the isotope will go. So half would be 50 grams. And after one half-life, you would have only half of the sample. If 2 half-lives go by, twice the time, then you're going to have half of that half. So half of 50 would now be 25, and you would be down here. So you're decaying. Now what's happening is the nucleus is breaking down and turning into something else. In this case, carbon-14 turns into nitrogen. It's a nuclear reaction, not a chemical reaction. And we can keep going. Half of 25 would be 12.5, and we can keep going until eventually we have very, very little left at all. Okay. Now the half-life, or time 1/2, for carbon-14 is about approximately 5,700 years. So that means after 5,700 years, only half of the original carbon-14 would be left. If we started with 100, half would be 50 grams. If you started with 10 grams, then only 5 grams would be left, but again, after 5,700 years. If 2 half-lives went by, then you would have half again less. So that would be only 25 grams left, and that means 2 full half-lives. So that would be twice the amount of time the original half-life would be. So that would be 11,400 years would go by. So what we can do then is we can use this to actually tell you how old a sample that contained carbon is. Now, carbon-14 has a very small half-life, so you can't tell how old, say, fossils are, because fossils are in rocks that are like dinosaur fossils that are millions of years old, tens of millions of years old. That's way too much time for this half-life. So in this case, you would look for other elements that are radioactive that have much longer half-lives, like in the millions to billions of years for their half-life, and then you can use to figure out, based on how much of the radioisotope is left, you can figure out how much time has gone by, and that gives you the age for the isotopes. Now the electrons are going to be arranged around the nucleus, and this arrangement of those electrons for a given element is what determines its chemical behavior. So it's very important to understand that structure. Now in the modern model, the electrons are arranged in orbitals, right? So an older model in the early 1900s is the Bohr model. It was named after Niels Bohr. And that put your electrons in very, very discrete orbits, the way the planets move around the sun. But the problem was that a good model should fit predictions. And what happened was when they used this model, they could not predict the wavelengths of light, the colors of light that would come off of atoms. Anything bigger than the simplest one, hydrogen. So right at helium and then any other bigger element that had atoms with a bigger nucleus and more electrons, it didn't predict it very well. So it's not a good model. But modern physics now has a newer model that places the electrons not in orbits, but puts them in orbitals. There's a difference. Now, these orbitals are three-dimensional spaces. They're described by mathematical equations, and this mathematical models actually make better predictions. So it is a better model, and it is the model that we go with. Okay, so if you look here, the models, it shows some of the simplest orbitals here. The very, very first orbital is a spherical one, and that's at the first energy level. Then at the next energy level, first energy level it's not an orbit. We're just going to draw a circle to say this far away from the nucleus. This is your first energy level. Again, it's not the same as an orbit, so don't confuse the two. At that first one, you're only going to have one orbital, okay, and it's spherical. And each orbital holds only 2 electrons. In the second energy level, the one further away, is going to have 3 orbitals. Again, each one holds 2. One of them is spherical. The other 2 are dumbbell-shaped, and they lie along different axes. So this would be 2 electrons held there, 2 electrons there, 2, and 2. And so that adds up to a total of 8. So we're simply going to draw each pair of electrons just along that circle to indicate that there's a total of 8 there. So your first energy level then, I'm just going to draw it as a ring around the nucleus, only holds 2 electrons. The next one can hold 8 electrons, okay? And when we combine all of the orbitals together, like we see down here, this is the energy levels for neon. Neon has an atomic number of 10, okay? And if we see there, atomic number of 10 means 10 protons here in the nucleus, 10 protons. and that means 10 electrons out here. And the number of neutrons can vary, right? So we don't know what isotope of neon, but we know that neon has 10 protons. So there's 2 electrons in the first energy level, corresponding to this one orbital. And then we have a total of 8 in the next one, corresponding to these orbitals here, each one holding 2. When we combine them all together, it gets to this really confusing thing. And so we start getting to bigger and bigger nuclei with larger elements after neon on the periodic table, and we start getting bigger and more complex. But these orbitals do predict what we see in nature, so it's a good model. Now to keep going here, I'm going to want you to know for sure up to the 3rd energy level. The next energy level can hold up to 18 electrons, but we're going to be good remembering 2, 8, and 8. So for now, just the 3rd level is also going to hold 8 as a maximum. So here's the idea for energy levels. Remember, the energy levels are going to be organized in 3-dimensional spaces that are described by mathematical equations outside of the nucleus, and those orbitals are arranged at certain distances away from the central nucleus, so they're going to have different energy levels. The further away you are, the more energy your energy level will have. So they do give them numbers. I'm just going to call the first energy level, they call it energy level K, the next one is L, and then M and N, and they just follow like the alphabet, K, L, M, N. So again, the first one holds 2 electrons, the next one can hold 8 electrons, and then 8. So it's really 18, but we're just going to say 8 for now. Now again, if you move away from one energy level to the next, and you go further up, that's going to require the input of energy. And if you come back down, energy is going to be given off. It's kind of like you're falling off of a ladder. You're falling back down to the ground. Right, so that's why they call them energy levels, because there's certain energy levels away from the nucleus, kind of like when you climb a ladder. You climb a ladder, you need higher and higher gravitational energy. If you come down the ladder, less energy. So it takes energy to go up. You give off energy when you jump back down. The last concept for section 1 is the idea of redox. And redox is short for oxidation and reduction reactions, or reduction oxidation. So we just call it redox for short. Now, to show quite simply how this works, if I were to look at sodium, sodium has an atomic number of 11, which means 11 protons. And that means it's going to have, if we look at the different orbital energy levels, the first energy level holds 2, the next one holds 8. That's a total of 10. So that means sodium is going to have one more, just one electron out here. It's 2, 8, and 1, like we saw in the numbers earlier. That one electron is the only one we're interested in. It's the electron in that outermost energy level, and that's all I'm going to draw here. That dot represents that one electron. There's still 8 in the next one below and 2 in the energy level right near the nucleus. So I'm just going to draw that one outermost electron. If we did the same for chlorine, chlorine has an atomic number of, which means number of protons, of 17. So again, that's going to be 2 in the inner level, 8 in the next level, and so that's 10, and then 7 in the 3rd level, and that would total 17. But all I'm interested in is that outer level, and that's all I'm going to draw here. So chlorine has 1, 2, 3, 4, 5, 6, and then 7. Okay. What's going to happen here is we're going to have an oxidation-reduction reaction when they react, like we saw earlier. In this case, remember, sodium is going to give up its electron, and the electron goes there. And when it does, the sodium now forms a positive cation. We're not going to draw any of the other electrons because it lost its outer electron. Those are the important ones. And chlorine gained that extra electron. It's now a chloride ion, and it's a negative charge. This diagram right here will help us simply see the difference between oxidation and reduction. An oxidation occurs when you lose an electron, and a reduction when you gain an electron. So which of these at the left of the reaction went through the oxidation? It was sodium, because sodium lost its electrons. So the sodium is oxidized. The chlorine, because it gained an electron, the chlorine is what becomes reduced. So over here, our chloride ion is the reduced form of chlorine. The sodium cation is the oxidized form of sodium, okay, because it fits those definitions. And this is quite simply what redox means. In any chemical reactions, electrons are moving around. They're either being exchanged from the metal to the non-metal. The metal gives it up. The metals are usually going to be oxidized and the non-metals reduced during that kind of reaction. We're going to see this more and more as we study chemical reactions within the cell, and it's important to remember that reduction means you're always going to gain an electron. This is something to remember for the future reference.